So, we are the Microgrid project team. My name is Peter. I have an associate's degree in electrical engineering and technology, and I'm completing a bachelor's degree in renewable energy. My partner TJ is working on a bachelor's degree in electromechanical engineering technology. We worked on this project together, but we're kind of present this in our own way. I'm going to go through the renewable energy part, and TJ is going to cover the load controller, which was his part of the project. So to get an idea of what a microgrid would look like on the VTC campus, you would start with renewable energy sources that would come and supply some kind of battery storage. And the battery storage would supply a load, being students using computers, air handling units, and anything that uses electricity on campus. If the renewable energy couldn't keep up with the load demand, a backup generator could be used to supplement power. So microgrid is a small-scale, independent utility disconnected from what we know as the utility. It utilizes renewable energy. It often has battery storage. It has a fuel-driven generator, and this all serves an electrical load. I like to think of microgrids being found in places like Alaska, way out in the bush, where it's not feasible to run power lines. So you have some renewable energy, you have wind and solar supplying a load, and if the load can't keep up, they have their diesel generator. Also, today, microgrids are being used to stabilize the grid, and they're powering small communities just like an individual house generator would. When designing a microgrid, you need to start with the electrical load. The electrical load is the energy consumed by buildings. It could be assumed or could be collected from the buildings in the area that you're trying to serve. You have to collect data from your renewable energy sources. You have to collect irradiance from the sun, which is a measurement of the energy that the sun creates, and you have to record wind speed. Wind turbines produce a certain amount of power at a given wind speed, and knowing that data will help with the design of the microgrid. You also have to understand what your options for fuel, if it's diesel or propane, and if you're going to have batteries, what kind of capacity are you looking for? So, in the renewable energy program, we can collect the data and we can come up with a way to model a grid. The collected data from the renewable energy sources can then be matched to supply a load. The load could be from the VTC campus, it could be from a house, it could be from the town of Randolph. And having this data and a microgrid trainer, this will allow students to work with the sizing of solar panels, the sizing or the number of wind turbines you would need, and using different size batteries. So for our load data, we decided to collect Green Mountain Power's data for the VTC campus. Now, what they collected was 300 to 500 kilowatts of energy used every hour. That was too much for us, so we scaled it down to 30 to 50 watts. So when the VTC campus is consuming 300 watts, our model is consuming 30 watts. Likewise, for 500, it would consume 50. This is why we're calling it a Pico-Grid. It's a very small, scaled-down version of a regular grid. I was lucky enough to find just about everything I needed to build this microgrid on campus. We had the AirBreeze wind turbine, we had the Evergreen solar panels, we have a controller from Vermont Energy Control Systems, we had the deep cycle batteries, we had the wind sensors. The only thing that I did purchase for sensors was sensors to measure current and voltage. And so that's the renewable energy side. TJ designed and built the load simulator, which he will get to at the end of mine. So the system diagram has several different paths. There's the energy path, the power path, DC current and voltage paths, an AC current path, and decision-making path. So we start with the solar panels. The solar array goes to a charge controller, which maintains battery storage. As the batteries are depleted by the load, the controller allows more power to flow from the solar panels. Next is the wind turbine. The wind turbine puts out AC power. So it goes through a rectifier to be converted to DC power. Our system is all run off of DC power. Our Vesta controller, provided by the Vermont Energy Control Systems, is our way of logging the data. And it gives us a way to monitor different parts of the system. So you can see that the Vesta controller is reading what the current and voltage sensor is sending out to it by both the wind and the solar. The other advantage of the Vesta controller is its ability to log data. With our solar radiance meter and our wind speed anemometer, we can capture every day what the power of the sun and the energy from the wind is doing and store it in a log file to be used for modeling. Next, we have the load supply module. This takes the energy stored in the battery and either switches between the battery bank and the AC backup power. The Vesta controller monitors the AC power and the current flowing from the storage batteries. Because we're using a DC system, an inverter is needed to convert the AC power to DC. And finally, we have the load controller. A data file in the form of a text file is loaded into a Raspberry Pi, which is our load controller. This load controller then varies the load between 0 to 50 watts. In this case, we're using LEDs. The Vesta controller can also keep track of the current that the load is using. The renewable energy concept was pretty simple. We decided to use the roof of green to mount the wind turbine and the solar panel. The wind turbine is a tilt-up tower made out of signposts, and at the top is the wind turbine with a wind vane and an anemometer to measure wind speed. The solar array, although it's hard to decipher this picture, faces south, which is pointing away from us. So the solar panel rack is made out of unistrut. There's a combiner box, and there are 3 190-watt solar panels. The rack is made from 3 triangles that I found were used for an old solar roof trainer. So I reconfigured them for my purpose and added 10-foot pieces of unistrut to attach the 3 triangles together and a place to mount my solar panels. The solar panels were wired with 10-gauge PV rated panels. Wires, sorry. The wires go into the combiner box where the 3 PV panels were wired in parallel. The combiner box also holds 3 20-amp breakers for my DC disconnect. The wires then go to the charge controller, which keeps the battery at optimal charge capacity. The battery bank are 2 6-volt batteries wired in series and have a capacity of 220 amp hours. To calculate the number of panels I would need, I chose an average load of 45 watts. Multiplied by 24 hours in a day, I came up with 180 watt hours per day. Dividing this by the assumed efficiency of the system of 85%, the battery voltage and peak sun hours, which are how much energy in the day of sun there is, I came up with 26.5 amps. Calculating the number of panels in series, I would need 1 panel in series and 3 panels in parallel. To calculate the battery bank, I first found the required amount of amp hours to supply the load. I then calculated the rated battery bank capacity, taking into effect the depth of discharge, is how far down the batteries could be drained, and derating factor. I then selected a battery with the proper voltage and rated capacity. As I mentioned, I used 2 6-volt batteries wired in series to give me 12 volts with an amp hours of 225. I finally then calculated how many, oh, that's what I just said right there. I needed 2 batteries in series and 1 in parallel. This is the Vermont Energy Control System. This is a web-based interface that allows the connection of both analog and digital inputs and outputs. I'm using this for the collection of data of voltage and current from the solar panels and the wind turbine, along with reading the inputs from the solar radiance meter and the wind speed anemometer. The advantage of this controller is that it allows for data logging. Every day it saves a data file. I have set to take a reading every second, which creates a very large data file, which you then have to dig through to adjust your numbers, and you can create graphs and whatnot. As long as you're on campus, you can just type in an IP address and get at the user interface. Outside of campus, you would have to do port forwarding, and that opens up another issue that we didn't want to get into for this project. This is the Autopilot. It's a sensor that measures current and voltage. On this side, you have the common or negative bar where the wires get soldered to. This is positive voltage in and positive voltage out. On this side is a 3-pin header. This is where you would send the scaled down voltage readings to your microcontroller. And right here is the shunt resistor. As you flow voltage across the shunt resistor, a small reading is taken by this Texas Instrument chip, and the current is calculated and sent out through these pins. this whole unit is capable of handling 90 amps of current. I'm only drawing like 30 amps, so it's a little bit oversized. It's used in the robotics field, but I found it to be perfect for my application. A solar radiance meter can be made by using a small solar panel. As the solar panel creates energy from the sun, a small resistor connected to a potentiometer is used to calibrate the relationship of solar radiance, which is in watts per meter squared, to the output voltage of the solar panel. On a bright sunny day, a solar radiance meter could say something like 600 watts per meter squared. By scaling down the voltage with a resistor and using a potentiometer in a multimeter, you could adjust the panel to say 6 millivolts, and that would equal your 600 watts per meter squared. This would then get sent to the Vantage controller to be stored as data. So what's still to come? I still haven't built the irradiance sensor that I just described. I'm still working on building circuitry for converting the AC frequency of the anemometer to a 0 to 5 volt DC reading that the Vantage controller is looking for. I still have some fine calibrations on my current sensor, current and voltage sensor. I have to do some battery discharge testing. I've run some lamps with a plug-in timer, but it's hard to say exactly what they turn off, and using the charts in the Vantage controller has made that more useful. And prepare for summer storage. We hope to use this next fall. I won't be here, but somebody will use it next fall. And so we would like to get it at a point where it's going to safely record data, and it would be useful for students in the fall to use for their modeling. Because my equipment was large and is mounted on the roof of Green, I wasn't able to bring it here. But I will be giving a tour after this presentation. If anybody wants to come over to Green 111 and take a walkthrough, I'll be happy to show it to you. At this point, I'm going to hand the microphone off to TJ, and he's going to talk about the load control.
So the problem for the load simulator was to design and build a physical load simulator that is capable of being easily changed to simulate a variety of different load profiles, such as campuses, village, or apartment buildings. My solution to the problem statement can be divided into 3 parts. The implementation of real-life data using a flash drive to hold the data, a Raspberry Pi microcomputer, and MOSFET driver boards. 2, the load, which uses a combination of resistors and 12-volt automotive LEDs. And 3, a human interface, which is electrical enclosure and 3D printed building display. My overall task in the project was to create a device that would simulate the actions of people and their effects on a load profile. I've done this by designing the system to read real power consumption data from a flash drive and then outputting a corresponding load. In this system diagram, the people would be the flash drive and the micro computer. The MOSFET switching board would be the switches on the appliances. And the LEDs and resistors would be the appliances such as computers, lights, or refrigerator running. The first step in designing the load controller was to determine the size of the text file that the controller would be reading. The VTC power consumption data I received from Peter was on an hourly basis for a week's time. In order to calculate the theoretical size of the file, I had to determine the number of entries that will be read in 1 week, as well as the size of each entry in bytes. I came up with the figure 5 bytes because there's 3 bytes for the values 300 to 500, and then there's 2 extra bytes for a new line between the entries, a carriage read and a line feed. The Raspberry Pi microcontroller can only output a 3.3 volt signal, so it's impossible to turn on a 12 volt LED with that voltage. So some intermediate electronics are going to be needed between the load and the microcontroller. This is a circuit diagram of the MOSFET switching board. It uses, it takes the 3.3 volt signal from the micro and flows into this device, which is an opto-isolator. The opto-isolator gives the MOSFET transistor enough voltage to turn on the load. In this equation right here, I'm using the micro output voltage of 3.3 volts, the LED voltage inside the opto-isolator divided by the 470 volt ohm resistor in the circuit. That gives you 4.7 milliamps. Now that we know how much current will be drawn from the microcontroller, we can determine how many channels we'll be able to use in our system. The microcontroller has a maximum output current of 50 milliamps. So if you divide that by the 4.7 milliamps we got in the previous slide, we get around 10 channels. So we can have 10 different LEDs running. Here are some basic calculations. These are necessary for some of the design work that we'll be reviewing in the next few slides. It's a 50 watt system divided by our 10 channels. So we'll have 5 watts per channel on the MOSFET switching board. 5 watts divided by our 12 volt system gives us around 0.4 amps per channel. 12 volts divided by the 0.4 amps equals 29 ohms in total resistance. Since the 12 volt LEDs don't draw enough current to consume the required 5 watts per channel, we will need to place a resistor in parallel to achieve the correct current draw. As I said in the previous slide, the opto-isolator provides the correct voltage to turn on the MOSFET transistor, which is acting as our switches to the load. Again, this is the same schematic I showed in an earlier slide. So the microcontroller sends a 3.3 volt signal through the opto-isolator, which draws a 12 volt signal through the transistor and into the gate of the MOSFET. In this graph, you can see that if we need to draw 0.416 amps through the MOSFET, that we would need at least 4 volts at the gate. That's why we use this opto-isolator to increase that voltage way above it to around 11 volts, which would be up here. Our 3.3 volts that our microcontroller is capable of would be more around down here and wouldn't guarantee that it would switch on. Since the 12 LEDs don't draw enough current to consume the required watts per channel, some parallel calculations were done. I have 129 ohms of total resistance and 150 ohm resistance of the LED. When you do the math, you come out with a resistor of around 36 ohms. So to burn 5 watts per LED, we need to have a 36 ohm resistor wired in parallel. Here's a schematic of the resistor board I designed for the load simulator and a picture of the actual board. It's not a complicated design, and I could have easily wired these resistors in line with the LEDs, but it made for a nice packaging, and it helped dissipate a lot of the heat having it mounted on the board. This is my full Python code right here. It's quite long, and this is a blow-up version of it. Right here is where it reads the data from the flash drive with a delimiter of a new line. This would be where how many entries you're going to actually step through. Since we step through one every hour for a week, we got 168. And this is the first few lines of actual code where it starts at between 100 and 600 kilowatts, and if it is between that range, then it will put on this LED. I started at 100 because the cooling system I use consumes around 5 watts, so I started with 10. I decided to design and print 3D buildings to place over the LEDs so it would create a good visual for the load of our Pico-Grid. Here's a CAD drawing of one of the buildings. It's about 5 inches by 5 inches, and like I said, it really helps create a visual for our microgrid. You can see in this table that the temperature inside the building evened out around 7 minutes to about 57 degrees Celsius. The material we used for printing was PLA, which softens around 50 degrees C and starts to melt at 160 C. So I came to the conclusion that some ventilation may be needed. Since the resistors inside the enclosure produced a lot of heat, cooling system was needed. This is a formula for calculating the amount of airflow we would need to cool the system. So TU is the ambient temperature outside the box. The desired enclosure temperature is TI, which I said was 10 Celsius. T would be TU minus TI, which equals 11.1 Celsius. F is the altitude factor, and for here in Vermont it's 3.3. And QB is the heat radiated in the enclosure, which is 50 watts, and I use the safety factor of 2 to give us a total of 100 watts. V would be the actual airflow required to cool the enclosure. We ended up getting a result of 17.5 CFMs, and to put that in perspective, your computer at home uses a cooling fan of around 25 to 50 CFMs, so it's a very achievable number. So this is a picture of my enclosure, and the bigger holes are the sockets where the LEDs get plugged into, and I put some about 1/4-inch holes in between them to try to suck some of that air out and into the enclosure and out the exhaust fan. And right here are the holes I put in the actual buildings. So here's a picture of the enclosure and how it's laid out. You have the flash drive and the Raspberry Pi right here going to the GPI breakout board. The pins lead to the MOSFET boards, which are basically the switches in the device. And then we have our resistor boards, which draw enough current from the battery to make each LED consume 5 watts. This is one of the commercial options I found that we could have used for the project, but it doesn't have a good visual for the load like mine achieves with the 3D buildings and the LEDs. And notice the price of about $1,600. Here's the load simulator cost breakdown. Anything in an asterisk I repurposed and was at no cost to us. So my total cost, including the repurposed materials, would have came to $220, which is a lot cheaper than that $1,600 product. Now we can move over to our table and do a demo of the load controller.